So today we're going to talk about the containers. Um, what I did is I just started up a GoldSim model and went right to the help file and into using GoldSim elements and then using containers. And here I am at the main containers page here. I highly recommend that you go through and read this part of the manual when you get a chance. There's a lot of good information in here I think would be very useful even for those of you with a lot of GoldSim experience. In particular is the optional features that are here in the next page, and then subsequent pages here talking about most of the things we're going to be talking about today, but in more detail. So I highly recommend that. I'm sorry. Um, Here we go. Can you see my screen now? You should be able to see my screen now. I forgot to reshare. Okay, there we go. There we go. Thank you. Okay, so I was just saying how in our help file you can go into here under using GoldSim elements and then using containers, and then we have our features pages here talking about all the different features that we'll be talking about today. All right, so the first thing I want to do is show you or just kind of have a discussion about in general organizing your model and using containers to represent your organization of the model and your system. So that's really what containers are mainly for. And so if you look at the this table here, it shows you all the different types of containers that we offer, and it's really just adding options to the basic container, which is this open container here. So basically, the most basic functionality of a container, obviously, is to contain things, your other, your GoldSim elements to organize your model. If you didn't use containers, obviously your model would be just huge. It would just look like a whole bunch of scattering of elements all over the place, and you'd have to zoom out, and it'd be a mess, right? So we add these containers that allow you to organize it. The localized container provides a lot of capability that allows you to create objects in your model where you have scope, local scope within the container, which I'll talk about in a second. And all the others are really just added features to the first two classes that I just mentioned. Okay, so let me start up a model. And let's see real quick here, webinars. I'll just open up one more. Okay, so here's a model that I just downloaded from our library online, and I modified it a bit to provide you the ability to look at two different ways of organizing a model. They both work exactly the same. They both generate the same exact answer, but they look totally different. And what I'll do is I'll put them side by side so you can see what the difference is. Just turning off the browser window here. Okay, so on the left is a model that is organized more in a strict hierarchical view, in the same way you would probably organize a file system. On the right is a way that is dominated by trying to visualize the system that we're the physical system that we're modeling, showing actual the schematic of the actual flows of water in the system. So let me start with the one on the left. On the one on the left, at the highest level, well, they're both the same at the highest level, but at the highest level, we're showing the basic organization of the model. So we have that separated into inputs and the system itself, which in our case is a flow network, but it doesn't have to be, right? It could be any system that you're modeling. Model results, which could include charts and dashboards, for example. And I also have this mass balance check. So you could have any array of things, but it's really just kind of showing you in general the overall organization of the model and how the different modeling aspects are linked together and so forth. But it doesn't really show you the schematic of the system that we're modeling. Not yet. Okay. If I go into the inputs data, then you'll see there are more levels of inputs in there. If I go into the flow network, you'll see that I have more containers, but they are showing the physical system. I'm just going to move these things over a little bit so we can, because I just don't have a lot of space here on this little screen. So just move a couple of things around. Anyway, you get the idea. There are 3 ponds in this model. Move over like that. So there are 3 ponds in this model, and they're kind of just waters flowing in and out of all of these ponds in order to their ultimate goal is to manage the water, but also to get water to feed these 2 demands down here, A and B. Water is extracted from this stream where I have an upstream and a downstream. Water comes out of here and it goes into these ponds. What actually happens is water goes into this pond. It's kind of a small one, and when it overflows, it immediately spills into this one. But as it needs more water, it will draw water back from it. So it just kind of comes back around like a recycle right here. And then ultimately what we do is on a regular basis, we're sending water down to pond 2 in order to feed these 2 demands. It's kind of a very simplified schematic or simplified example of what you might find at a typical mine site or water balance system of some sort. Water that's used for B is all returned. Water for A is all consumed. The returned water from B is then split. Some is lost to the river and some is returned back. So anyway, the same exact thing is done over in this other model too, but I'll show you that in a second. If I drill into any of these containers, then you'll see there's more in there. So for example, if I go to the upstream container, I have these 3 elements that represent the upstream stuff, and it's really just information coming in. The diversion, how much water is diverted to the pond and how much goes to downstream. And if I go into pond 1, then you'll see I'm calculating the volume in there. I'm calculating some other things in order to determine how much water I need to pump out and in. I've got some natural phenomena occurring, evaporation, losses, and some overflows. Maybe these should, anyway. Okay, and then I can even go further down, obviously. So that's kind of how it works. So this little container here represents a physical object. So that's what's important to note about this container. You'll see here that one is closed, one is a closed box, and the other one is an open box. So I mentioned earlier that the open box is kind of the base default container, in the most simplest form. And all it does is you just put stuff in there, but it's global. That's why it's shown as being open. It means it's has a global scope. That means the name of any element inside there can be referenced or linked outside of this container with that same name. So if I go in here, you'll see I have a thing in here called diversion. If I go up to this global level, well, not global, one higher level, and if I try to create a new element and call it diversion, you'll see it tells me I can't because it's in the same scope as another element with that name, right? So it's a conflict. So we can't do that. I'd have to change it in some way in order to do that. Okay, but if I go to pond 1, which is localized, and I look in here and I see that, there's something called volume, then I could come out here and I could say, I want to call this thing volume, and it would be perfectly fine with that because the namespace inside the localized container is local. All right, what that also means is that when we do reference, let me first show you reference. So if I go in here and say I want to reference the diversion, meter liters per second, and then come over here, diversion, and 2 pond 1. So I'm referencing the diversion output from inside of here. And so it's telling me that it's looking at the diversion 2 pond 1. Actually, that's kind of a bad example. Let me refer to the upstream flow that's inside of there. The reason it's a bad example is because I have a dot there because it's an allocator. So let's skip that one and let's just go inside and grab inflow data. So there we go. So now you see it just says inflow data. But if I want to refer to the pond volume inside pond 1, let me do that. So I go to pond 1, volume, and what you'll see here, I need to change the units here. What you'll see here is that it says pond 1 dot volume, and so that's why I was saying that when you localize a container, it kind of creates sort of an object, and that lends itself well to object-oriented modeling, because what we have now is the object itself with a dot followed by an attribute of the object. So that's kind of nice that we have that. And I do see a lot of users building models like this, and it's definitely a good way to go because it does give you that kind of feel of having real objects in the model. Okay, so what we've done by accessing this attribute called volume, which is just really an output element. It's an element output inside of that container. What we've done is we've exposed the output called volume. There are some outputs inside of here that are not being used outside. For example, %full. And the reason I know that is because this output port does not have an outline around it. Notice how these do. That indicates that the output is being used outside somewhere. So if I wanted to refer to %full out here, let me go ahead and try that. Pond 1 dot. Notice how when I type pond 1 dot, it auto-completes to show me all of the exposed outputs that are available right now. Oh, it looks like %full is actually one of the outputs that's available. So if I go ahead and type that, then put that in. I just need the right units, and then that will work. Okay, so if I double click on the container and I go to the exposed outputs tab, then you'll see it lists all of the exposed outputs. I can, by the way, change these if I wanted to. I'm not sure why I would want to in this case. Every once in a while, you need to create a new alias for something that's inside here. Usually it happens when you have double containment with multiple localized containers inside of one another, where you could end up with a name conflict. GoldSim will always resolve those if you're inside of localized containers, but it could be that you would have, and what it will do is it will say volume _1, volume _2, or something. If you have multiple localized containers inside of another localized container, GoldSim will just assign a number to it. But if you didn't want numbers, you could change it, and that's why we allow you to change or create an alias with a different name than the actual output. So now what you'll see here, pond 1, you'll see that volume 1 now has been changed, or sorry, the word volume has been changed to volume 1 because I changed the alias of that. Okay, so if we go around the model, then you'll see that in each of these containers, they're very similar, all of these containers. In fact, we could even clone these containers. I'm not going to talk a lot about cloning today, if at all, but I have done so in other webinars if you're interested. But inside of each of these, they're all doing a very similar thing. But one thing I want you to notice is the naming of the elements inside of these containers. Notice this also says volume, but we are in a different pond. I don't need to say volume 2 or volume pond 2 or anything like that, because we see up here in the container path that it says flow network pond 2. We already know we're in pond 2. To be even safer, I would probably add some text up here, big bold text that says, hey, this is pond 2, etc. Something, text like over here, I'd put text there. if this was a real model. But anyway, so in each of these models, you'll see that they all have the same names of things. And that's by design. We want that, right? We want it to be generic inside of the object itself, because they're differentiated by the name of the container. If I went in here and I said, this is pond 1 underscore volume, or even worse, pond underscore 1 underscore volume. If I did something like that, and then we come up here and we say, oh, now I want to reference that that volume, then it gets a little bit messy, right? So let me do that. Pond 1, and then you see the name, how it's just totally redundant, right? Pond 1 dot pond 1 volume. So once we have a localized container, you really don't need to be redundant like that. Just say what the attribute is of the thing that we're talking about, and then it will look much cleaner. Okay, so there are a lot of positives about this approach. One negative about this approach is that, or one challenge, I guess I should say, one challenge with this approach is that it could be more difficult to fully understand how the water is flowing here. And you might be saying, well, no, it's obvious, the arrows are pointing. Well, it's not exactly true, because look at this expression I just created. All I did was refer to something in here, and I'm not actually saying water is flowing this way, right? Another thing here is that I have an arrow going forward and backward between pond 1 and 2, but that's not actually what happens. Water is only flowing from this pond down to this pond. It's not going back. It is on these two up here, but it's not in this one. And you probably all know the reason for this. It's because I'm referring to something here in pond 1, which causes an influence line. So as you know, having used GoldSim, that GoldSim draws influence lines that that's all they are, is it's just influences. And so GoldSim doesn't know the difference between, water moving and referring to some variable somewhere else in the model. They're all treated as just influences. And if I double click on this line, not only is it not water moving, there are two things inside of that line that are moving, or that are not moving, that are being influenced. So this particular schematic here should not be literally described as a flow network schematic. It is a system, I guess we could say system logic influence, or logical influence schematic, or something like that, right? Now, one thing we could do is just color code these lines. Could say, do something like that, where it becomes more obvious that, and this is just because I, as the modeler, know where the water is going, and I could color them and say, well, yeah, water goes there and there. Even though if I click on this line, okay, that's a bad example. On some of the lines, if I click on them, you'll see there's more than one thing moving. Well, okay, this is the only one, this red one, but in some cases you might see that there are multiple things in there. In your real models that you build, you'll probably see that you have many more influences within a single line. But anyway, you could do something like this, and it shows you, yeah, the water is moving in these directions, except for any other non-blue lines, for example. By the way, you can globally change these influence lines if you didn't know. Going here to properties, and then you just change the lines, so forth. Okay, so that's that model. Now we go over here, and like I said, this is exactly the same model, but it's organized in a completely different way. So what we do with this model is, if when I go into the flow network, and unfortunately I'm using such a smaller screen now, kind of have to move a lot of these things around. Let's see. Or I guess I could just expand it all the way. How about that? Okay. All right. So this is doing exactly the same thing, except every single influence line in this model, or in this page, is water. They all represent water. And you can also see I have no containers here. And the reason for that is because I'm trying to show only, I just want to focus on just the water here. There are a bunch of auxiliary calculations going on in order to figure out what those flows must be that move around, but that's done up at a different level. That's done in the inputs. So if I go all the way to the top, you'll see here, this is the key difference. This little arrow right here that goes back. So let me compare it to the other one. Go back up here. So see how this only has one line going that way? That means it's just data driven, right? So we just have static data. Well, it doesn't have to be static, but we just have an input feed in this container, and it's just going one direction right into our flow network. In contrast to that, this model here is not only feeding the flow network, but we're also carrying state. So the flow network has state associated with it, right? So there's always some amount of volume in these ponds, and that amount of volume is being used to figure out what we need to do on the next time step. And so that information is transmitted back over here, and saying, okay, hey, the reservoir level is getting low. We need to do X, Y, and Z. So do those things, and then it transmits that information back over to here to say, okay, now I want you to open up the gate more. I want you to turn on the pump higher, or whatever, or turn the pump off. So that's kind of how it's working. And in essence, all I've done is just moved a lot of the auxiliary calculations out of the flow network to really just focus on just the flows. And this is a method that I actually don't see this very often in models that I see on a daily basis, like the other method. It doesn't mean that it's wrong. It's just another way to do it. It depends on how what you need to focus on and show your audience. Personally, I think that in some cases this could be a very powerful way to show your audience what's going on in the physical system. The downside is that in order to understand what is driving these flows, you continually have to go back, right, to that input folder to see why it's doing what it's doing. So, trade-offs there, it just depends. Okay, so what we do here is, and let me just show you an example. Right over here, we're saying we have pond 1 discharge that goes into pond 2. Well, how do I know what that flow is that goes into pond 2? If I open up this allocator, you'll see here that I have this thing called pump 2 request. So that's what's driving the flow to come out of pond 1 and go into pond 2. And you'll see that pump 2 request is also in the, well, it's over here, it's called, sorry, that's the addition rate. Pump 2, there it is. So pump 2 request. I also have some evaporation, which don't really need to worry about, but pump 2 request, that's what's being withdrawn from this reservoir. But it's dependent on the state of what's happening in pond 2. We only want to send water down there if it's getting empty, right? If it's starting to fill up and get too full, we'd just turn that pump off and we wouldn't send it down there. So in the first model that I showed you, this one, I go in here, it's well, actually we have the pump sitting at pond 2, I think. Here we go. So in here I say, okay, remember I mentioned if the volume is too high, then turn that pump off. We don't need to bring any more water in and so forth. Then I go into the pump here and it shows me what the status of based on the status of the pond. And here we're saying if the volume is less than the operating target, then turn it on. If the volume is greater than the operating target, turn it off. That's all that the status does. By the way, this is a very good way to control flows in and out of a pond. In case you're wondering, I would always consider using a status element if you can in your models. And the reason for that is because all you do is just trigger it when to turn on, just like a real pump is triggered, or like a real thermostat is used to trigger a furnace or air conditioning to turn on and off. And once it's turned on, it stays on until you turn it, tell it to do otherwise and turn off. It's very useful. It allows you to put in a deadband so that it will stay on even though it's dipped, slightly above or below your target. So very important for control theory with feedback. Based on the status of that, it's true or false, then you tell it what the flow needs to be. So if the pump is on, then it's flowing at the pump capacity, otherwise it's 0. So that's how that works. And it's all located inside of pond 2. Okay, compare that to what we have here. So in here, we say, okay, we have this pump 2 request. Well, what is that? Well, I've got to go find it. It's very easy to do that. You just simply right-click on the element, go to function of, and you'll see there it is. And here we have the exact same thing. So this is doing exactly the same thing. Something else that's sort of nice about putting all of the attributes of the ponds over here and all the auxiliary calculations all in one place is that I can just do them as a vector calculation. So I might have, I have 3 different ponds. That means I have 3 different initial volumes, 3 different operating targets, 3 different pond capacities. I might also have 3 different stage area curves or stage storage curves. I just created one for all of them for simplicity. But what that means is my auxiliary calculations can be done as vectors of these 3 as well. So I can calculate from that 3 initial volumes, calculate from that 3 initial, and 3 I can, during the simulation, the pool area is changing to calculate evaporation, but I have 3 of them that are calculating all at once. It's just a vector expression. So there's 3 ponds, but it's just a very simple calculation, and I'm doing that for all 3 ponds at the same time. I don't need to do this. I don't need to create 3 of these guys, right? There's no reason for that. I can do them all as a vector. Conversely, we look at this other model, and we'll see that inside pond 1, I'm calculating the pool area. I go to pond 2, and I'm calculating the pool area again. So it's replicated, right? So there's a bit more repetition there. Okay, so I hope this kind of gives you a good feeling for how the model can be organized in a different way. And I hope it helps for you when you work on your next project to kind of consider these kinds of options you would be looking at when you're designing your next model. All right, let's talk about some of the options, features of containers. All right, so first of all, when you open up a new container, you're presented with the properties page here, and it shows you what the optional features are. Right now, none of these are checked. Somebody asked, does vectorizing as shown in Model 2 allow for faster calculations compared to Model 1? Really good question. So I've not done any benchmarking like that to test. Usually I've tried benchmarking a few of those kind of things like that, but it's always more complicated than it sounds to do benchmarking. There's always so many variables that I don't understand. I'm not the one programming this, or programming GoldSim. But I do know that working with vectors in GoldSim is extremely fast. We're using some very low-level C libraries to work with arrays in GoldSim. So my experience has been that even working with very large arrays and doing for loops and iterating over them, which is essentially what you do when you vectorize an expression, you don't actually see it. You don't think it doesn't look like you're writing a for loop because you're not, but under the hood, that's what it has to do, right? It has to iterate over the array of ponds and do that calculation over and over. So that part of it is quite fast. And so my guess would be that it could be more efficient to have vectorized equations than to have multiple elements. Just my guess, but I have never actually tested it. Okay, good question. Thank you. So here we are at our container properties, and you can see that if I hit localize, it just changes it to localized. That's the only difference there. But the next options here will, when I check them, see how it's in a hierarchy here. So if it's below the thing here that's called treat as subsystem, it means that if you check any of these, then it must be a subsystem. So if you see, if I say conditionality, then this this also becomes a grayed out checkbox. I cannot uncheck the subsystem and still have conditionality. What it says is, no, this has to be a subsystem if you do this. Well, what's a subsystem? Well, that's an excellent question. And what I would say you'd want to do is read our manual about it, and you can always do that by clicking on help in the context that you're looking. And I don't want to go terribly into it, but you will be able to find it in there. Essentially, what it means is it doesn't mean it's a submodel. So just keep that in mind. Somebody asked that in the morning session. The submodel is very different from a container, and a submodel is really just another GoldSim model that's embedded in here. Totally different thing. But a subsystem, what it's doing is it's affecting the causality sequence. So if you're not familiar with the causality sequence, let me show you. Causality sequence can be reached here by clicking on model and then going to causality sequence or typing F10. When you go there, you'll see a whole listing of names. These are all of your GoldSim elements. And you'll see that the one I've selected, the one I selected before I went to the causality sequence, is bold. And it's first on the list. GoldSim it tries to figure out what the causality sequence is. You don't want to be messing with this. Not that you really can. You do have the ability in some cases to push one element behind or in front of another. In some isolated cases, you can do it if you need to. A good example of that is when you have two events in your model, like let's say just two triggered events, and they're both defined as trigger on E-day, or no, trigger every Sunday, let's say that's all you said in there. Well, which one happens first in the sequence? That is an ambiguous sequence. And GoldSim tries its best and figures out, okay, I'll just randomly pick one. It's not really random, but to you it looks random. Well, you can actually switch which one of those would happen first. So events is a good example of where you'd have ambiguous causality sequence. But for the most part, you don't have to mess with it, so don't really worry about that for now. But one thing I did want to point you to is that a container can be listed in the causality sequence as its if it's its own element. And the way it does that is if it's defined as a subsystem. So essentially what happens when you create a subsystem is it says, okay, I'm my own element. I'm not coupled with anything else outside of me. I'm just my own little person sitting here. And I act just like any other element in the sequence of calculations. Now I do have a whole sequence inside of me, but in regards to people outside of me and next to me, adjacent to me, I am my own element. So that's why it's important to understand sequencing when you're thinking about subsystems. Okay, so let's say I want to have some conditionality on one of my containers. Let's go into this flow network and let's just say, I don't know, pond 3. Let's go in here and say, well, there's a pump here that's always operating. Well, that's not exactly true. It's got an on-off switch here, but it's always assumed to be operational. Well, we could use conditionality on the container to simulate its availability, let's say. Now we're getting into the reliability module, which let me just show you really quick. Reliability module, and that's where you get into stuff like what I'm talking about, where you have availability and failure modes and all that kind of stuff. But let's not worry about that. We're just going to do something simple. So what I want to do here is I want to say, well, this pump has a period of time where it's not even available. Even if you wanted to turn it on, you couldn't. So what I could do in here is I could say, let's create a couple of events. Let's say on day 50 at E time 50 days, it says become available. And then we have another one just like this that says unavailable. And then we say at 70 days, like that. And then what you could do is you could go to the container here and you could say, I want to make this conditional. and I want to activate the container, the whole container. That means everything inside of it, and I'll activate it. Let's see if I can do it on something that's inside. I didn't actually do this in the morning, and it has to be outside. Okay, so let me put this on the outside. Should have known that. All right, moving those out. Okay, I guess that makes sense because it wouldn't be able to do something if it's not active. What I'm doing is I'm saying I want everything inside of this container to be active when I tell it to, and that's this event here. But I also want it to become inactive when I click on this one. Now, be sure you're listening to my words I'm using. I'm saying active and inactive. Okay, I'm not saying turn everything to 0 inside of here. So this is what confuses a lot of people, and I'm going to do something else in here. I'm going to create an expression here that says sine of eDay. Okay, so this is just a continuous function. That's just, as you should see, like a sine wave, right, through time. But it's not going to be 0. Well, in fact, I'm going to do this a little bit differently. I'll say eDay plus 3, just so it doesn't start at 0. Okay, and let's just redo that for now. So I run the model, and by the way, with conditionality on a container, I can click on the output port, and I have all these outputs that are available just about the container that tells me the status of the container and when it became active or when it stopped and so forth. Okay, so somebody asked, can you show me how you created the trigger element? And I can certainly do that. The trigger is just here in the events, and it's called a triggered event. And that's what I did. And I just went in here to the triggering. So there's the trigger button. I just go there and I say add, and there are lots of different ways of creating triggers, right? So one of the ways is add e-time, and that's all I did. I said at e-time 50 days, like that. So, all right. So that's going to trigger this pump, and there might be in a real model, right? There might be a lot going on in there, but I just want to say it becomes available at 50 days. All right, so I run this, and now I go in here, and I look at the pump request, and I see that it turns on at 50 days. So what this is, oh, you know what? Hang on, this might be left over from this morning. Let me just check something here. Ah, yes. It turns out that from this morning I said make it unavailable after 70 days. So just know that I did that in the status. But the important part is that, it is turning on. The pump is turning on day 50. So you see it's turning on day 50. Even though it probably wanted to turn on earlier than that. But it couldn't until day 50. But what you'll see though is that what we have here is we have the sine wave is not doing anything. It's just sitting here at 0. And I forgot that it has to be starting at 0 because that's just, it initialized without calculating anything yet. So it just had to start out at 0. But what's important to note is that if I have this container deactivate again at day 70, it's not going to make this become 0 again. It won't go back to 0 necessarily. It will just deactivate. It will just not do anything. And so it won't go blank, but let me show you what it does. This is usually what's a surprise to people. So now I'm going to deactivate the container on the unavailable trigger. So now you see these two triggers are causing the pump to be available and then unavailable. So I run this, and I go in here and I look at my sine wave, and you see that it didn't go back to 0. So that's what's important to note here. Well, first of all, making all of our outputs go back to 0 is arbitrary, right? I mean, why 0? Why not 999 or negative 999 or something? No, it doesn't do that. Well, all it does is it says, I was calculating something, I was going on my merry way here, and all of a sudden I just didn't update anymore. So I just don't do anything. It just stays there static. So that's what happens when you activate and deactivate a container. What that also means is if I asked the pump, and I'm going to go in here and modify something. This line is not supposed to be here. Okay, so now if I operate this, if I'm operating this pump, it says, okay, I became available on day 50, and it's just sitting here on day 50, and it's just on, it's on, and then all of a sudden we say, okay, deactivate the container. Well, it doesn't mean we turn off the pump. We don't tell that, we're not saying physically reach into the pump and do something. All we're saying is just ignore any other signals that are going on. Ignore everything. Just keep everything as it was, and don't touch anything. It would almost be like, it's not like turning the power off at a pump station. It would be more like having the operators just walk away. That's what it would be like. And so what might happen here is that the pond might start to overflow, right? Because you walked away, and it's no longer operating. That's how you have to think about how the conditionality works on a container. So I hope that makes sense, what I was saying there. Yeah, so that's the pump volume. Okay, so that's conditionality. The next thing to look at is the internal clock. Okay, let's go over to pond 1. If we run this, if we run this model again, and we plot the volume of pond 1, what we see here is that we're hitting the upper bound of 4 cubic meters, and we're also hitting the lower bound of 0 multiple times. Okay, so what happens in GoldSim when you hit those bounds? This is something that you would never, well, it doesn't really come up in let's say a spreadsheet type of model, because you don't really deal with events in a spreadsheet model. And so this often comes as a surprise to new GoldSim users, and it's very important, this topic. So let me try my best to describe it, but we do have a lot of examples that and articles that talk about this. If I go to the tabular view, you'll see that there's a time step of 1 day usually, but there's also inserted steps. You'll see one that's right here, 1.008. And you'll see that the volume is 4. Well, that's right when it hit the upper bound. Right exactly at the moment it hit the upper bound is at day 1.08. So it's a little bit after day 1. You see it got close on day 1. It got to 3.9, but it didn't exactly get there until just after. So what GoldSim does is it inserts a time step. What that also means, though, is if I look at any other output that's totally unrelated to that reservoir, okay, I'm in a totally different place now. I'm looking at the downstream river flow, having nothing to do with that pond that's way over there, but you'll see I still have this line item here, 1.08. Okay, what that means is that when you hit bounds in a reservoir and that has global scope in your model, which ours does, not global scope, I'm sorry, which is not contained within a container that has its own clock, the time steps that are inserted are seen everywhere in the model. And it's okay. I mean, it's not causing any problems. It's not making any errors in your model. It's perfectly fine, and GoldSim will operate just fine. And also, by the way, typically by default you won't see all of these things happening, because typically you'll be here in your simulation settings in the advanced tab here, and you'll probably have this unchecked right here where it says include unscheduled updates, right? If that is unchecked and you run your model, you will never know. You'll see none of those inserted steps show up. So this is oftentimes a revelation to people that that have just starting to use GoldSim. And so I just want to make sure that you see this. And also you see here that, okay, on day 2 it says we're at 4. Well, it didn't take a whole day to get from 3.9 to 4. Even though I suppose if you were to zoom in here and look at that, that might be what's concluded. See how the slope of this line changes between day 0? Well, I zoomed way in here. Hang on. Reset. Let me just do this. Okay. So see how we're on a trajectory Well, that's even worse. That's not helping. Okay, so we're on a trajectory here going at this slope, and all of a sudden it flattens out and goes to 2 like that. Well, let's look at what really happens here. Okay, so destroy results, go here, include unscheduled time steps, run the model again, and then zoom back in. And what you'll see here is that it's coming up and it shows you exactly the point that we hit the upper bound. Not at 2. Okay, so that's how GoldSim works by default. And I'm getting into a whole nother topic here, so I'm not going to spend a long time on it, but I just want to note that if you have to, in some cases, you don't want this to happen. You don't want unscheduled updates. So you could uncheck this and run your model, and you will see it will work just like a spreadsheet. I think I have a problem with my mass balance now because I need to change something, but it's okay. We can fix it if we have to. But what you'll see here is that it does actually apply an average. It knows that there was where we hit the upper bound somewhere around 1.08. It knows that that would happen, or that it did. But what it says is, well, I'll just assume that the average of that little tiny time of flow will be spread out over an entire day. And that's how you do it in something like a spreadsheet model, and that's fine. So some people, they have to do it that way, and that's fine. That's why we have that option there. But let me undo that. We don't want to have it that way for now. What I do want to show you, though, is that there are some parts of your model that you do want to have smaller time steps, either through events like I've just described, where you hit bounds, or triggered events of your own, random events possibly. Let's say maybe you're simulating an earthquake or some random event that, or some failure that happens. Those, if they happen randomly, then you can't specify an exact time, right? So you would want to allow events, inserted time steps. Well, if you need some portion of your model to have a smaller time step, then the rest of the model you use an internal clock. So that's where we could come to this container, the container properties, and click internal clock. So now what that allows us to do, now when we run this, I go inside of this container and look here, you'll see that there are the inserted steps here inside, but if I go outside, it's not there. There's another one, but that's from some other thing. But the one I was showing you earlier, the 1.08, it's not here anymore. It's because we've kind of isolated it. We've insulated it from the rest of the model by creating that internal clock. There are other reasons for internal clock. Sometimes you need to do something that's just more detailed on a smaller time step that's defined. Like, what if you needed an hourly time step in one portion of your model? Then that's when you would use an internal clock. But keep in mind, again, very different from a submodel. Here's a submodel right here. This is like a whole other GoldSim model. It has all the same features of a GoldSim model, but it's inside of a model. That's for a different topic. That's for a whole different webinar. Okay, so that's the internal clock. All right, last is the looping. Looping is a bit more complicated to describe unless you've done a lot of for loops and maybe iterative type solvers. If you're familiar with those, then the looping container will probably make total sense. But for me, it was a bit different when I was first learning GoldSim. It took me a while to wrap my head around what exactly a looping container is doing. But you do kind of need to think of it like a for loop. When you write your own for loop, you have it iterate, right, until some condition is met, or while some condition is true, right? And that's the same way you would do it with a container. So in a container that's got looping, which I'll do now, looping. Now if I come over here and I can put in some condition, I'll do until. It's just like a while loop or a do until type loop. I might want to say I'm going to do this until my loop count, which is a known property once you have a looping container. I want to do it until my loop count is, I don't know, greater than 3, we'll say. That means that on each time step of the model, it will recalculate the stuff inside of there 3 times, actually 4, because it goes 1, 2, 3, and then it waits until it's greater than 4. So it would recalculate everything in there that many times. If you don't have anything in there that is referencing the value in the previous loop, I'm not sure it would be very interesting in there. But if you are, then it can provide you a lot of capability. But it is very advanced. We don't see this very often, but there are some cases where it could be very useful. One is, I've already mentioned, for doing an iterative solver. Another one that is kind of a kind of have to be a little bit careful with, but it could become very useful in a flow system where you have recursive loops. It could be very useful. So let me show you that. I'm going to go over to the other model to do it, this one here. And the reason is because it doesn't have so many containers. But let's say, for example, that, see how I have this flow loop over here between pond 1 and 3? It's going around in a circle. Let's say, for example, that you don't want there to be a delay in this flow. It's just a continuous cycle. The flow that comes over here into pond 3 immediately comes back. And this happens when you have large time steps and small volumes in your ponds, relatively small. And so having a delay of a whole time step could maybe it's not so realistic. There is a way to avoid that. Well, there are a couple of ways. You could, well, probably more than a couple, but if you had a flow solver, you could do it that way. But like I said, solver, that means we're iterating, or we're solving implicitly, I mean, to get to an answer. Well, if it's just a simple flow network like this, one thing we could do is, instead of using a delay element, I could use a previous value, which, as you know, just grabs the value from the previous update in time. But if you have looping, it actually references the value from the previous loop, well, or the previous update, depending on if you're at the end of if you're doing the very first loop, it would be the previous time step. But on subsequent loops, iterations, it's going to grab the value from the previous loop, which is very important, because what that means is it will eventually come to be the current value, the current time step. Okay, so it's kind of a way to warm up to be a continuous process here, feedback process. So it's good for like process models and so forth. All right, so I'm going to remove that guy and replace it with this one by pasting in the same name. Hit F9. Oh, I'm going to have an issue with my mass balance now. Let me just delete this guy out of here. Don't worry about the mass balance at the moment. Okay, so now what I'm doing is I'm saying I still want to grab the value from the previous time step and send it over here, but I want to loop this container so that instead of grabbing the value from the previous time step, I'm grabbing the value from the previous loop. And that would become immediately the same number as the current value. If I run this now, I haven't started looping yet. So what I'll do is I'll show you. This is the return flow now compared to, sorry, this is the previous value of the return flow. And let's see, pond 3 discharge to pond 1. Okay, this is the current, and you can see there's a delay, right? So they're not aligned. And most of the time this is fine, right? I mean, it's not like it's a huge error in the model, and there always are delays in flows as you're sending them one way or another, but sometimes it's just an annoyance to put it in there because you have to explain this to your audience, and it's hard to describe, and so it might be good to try to clean that up a little bit. So we could do that by looping. So let me go up here and turn on looping. Loop until loop count is greater than 3. Run the model. Okay, I didn't mean to do that. And the results are going to be slightly different because we are we're sending immediately the feedback that comes back around again. But anyway, pond 3 to pond. So you see they're right on top of each other now. So anyway, so that's one way to get around feedback in a system like this. Anyway, so that's 3 different options on your container. I didn't, oops, let me destroy my results. I didn't talk about resources. You can read about those. There's also protection, and that's just a way to password protect changes that are made inside of your model if you want to. So that's the end of the presentation. I hope that was useful. Thanks a lot for joining, and I will take questions at this time if you have any.